Another one of the things that we looked at in Chapter 5 was the special case of multiplying two binomials that were identical. One way to write a plus b times a plus b is a plus b squared. So when you see a plus b squared, you can think a plus b times itself. When you use distribution on this, you end up with a squared plus ab plus ab again plus b squared. And this is a shortcut. If you had, for example, x plus 3 squared, you could write it as x squared plus 2 times x times 3 plus 3 squared. And that simplifies to x squared plus 6x plus 9. But you can also just use distribution. Just recognize that x plus 3 squared means x plus 3 times itself, and then distribute. X times x is x squared. X times 3 is 3x. 3 times x is 3x. And 3 times 3 is 9. Combining like terms, I get x squared plus 6x plus 9. So whether you use the shortcut or whether you just use distribution, you'll end up with the same answer. In this section, we've already looked at the difference of two squares and talked about how recognizing that pattern can lead you to the factored form of a polynomial. If you just recognize the factored form the polynomial must have come from before it was multiplied. We can do the same thing here. For example, I can factor this by recognizing that it's in the form x squared plus 2 times x times 4 plus 4 squared, which means it must have come from a binomial squared, specifically this binomial squared. To double check that that's right, I can distribute. X squared plus 4x plus 4x plus 16 is x squared plus 8x plus 16. So this can be factored like this. And of course, this can be written like this. So these are equivalent. But as with the difference of two squares, we can also use factoring by grouping. Let's start again with x squared plus 8x plus 16. Now we know to look for a greatest common factor before we start factoring. There's no x in this term, and there's no number in this term except for 1. So there's nothing common to all three terms. Having decided that, let's go look for our product and our sum. My product is 1 times 16. My sum is 8. The ways that I can write 16 are 1 times 16, 2 times 8, or 4 times 4. These ones add up to 17. 2 and 8 add up to 10. 4 and 4 add up to 8. And that's the one I want. So these are the numbers that I'm going to use to split up my middle term. Let's rewrite the problem, but instead of 8x, I'm going to write plus 4x plus 4x. Notice that the difference between this problem and the one before it is that with the difference of squares, one of these would have been a plus 4x and the other one would have been a minus 4x. Not only that, but this would have been a negative as well. What's common to these two terms is x, and what's left over is x plus 4. What's common to these two terms is 4, and what's left over is x plus 4. What's common to these two terms is x plus 4. And what's left over is x plus 4. Because in this form, this is a binomial times itself, I can rewrite this as x plus 4 squared. These are equivalent. On an exam, I won't care which of these two you give as your answer, but it's really handy to be able to convert back and forth. Know that when you see a binomial squared, that it can be written as that binomial times itself. But also know that when you see a binomial times itself, you can write it as that binomial squared. Later on, that's going to come in really handy. My point here is that again, I have the choice between this shortcut and factoring by grouping. Factoring by grouping works on any trinomial as long as it can be factored. As you do the textbook exercises in this section, for part B, you'll notice that all of your answers can be written in this form. But that's because they're from this section and this part. They're all about recognizing this pattern. Let's do another one and I'll show you what I mean. This is question number 38 from your textbook. A squared plus 10a plus 25. If you can recognize that this can be written as a squared plus 2 times a times 5 plus 5 squared, then you're ready to take the shortcut that this is a plus 5 all squared. If you're not sure, you can always multiply it back out. A plus 5 squared means a plus 5 times itself. A times a is a squared. A times 5 is 5a. 5 times a is 5a, and 5 times 5 is 25. Combining like terms, I get a squared plus 10a plus 25. That's what I started with, so this is the correctly factored form of this polynomial. I don't need anything down here. I just did this work to check that this was the correct answer. A plus 10a plus 25 can be written as a plus 5 squared, or a plus 5 times itself. If you're not sure about that, then just do it the other way. A squared plus 10a plus 25. What's the greatest common factor? 1. There's no a here and no number here except for 1. So there's nothing that's common to all three terms. My product is 1 times 25. My sum is 10. Everything's positive. 1 times 25 and 5 times 5 are the only ways to write 25 as a product of two numbers. 1 plus 25 is 26. 5 plus 25 is 10. That's the number I want. So 10a becomes 5a plus 5a. The greatest common factor of the first two terms is a. What's left over is a plus 5. The greatest common factor of the last two terms is 5. What's left over is a plus 5. 5 times a is 5a. 5 times 5 is 25. The greatest common factor of these two terms is a plus 5. What's left over is a plus 5. A squared plus 10a plus 25 can be written like this. A plus 5 times a plus 5. Of course, that's a plus 5 times itself, so we can write it as a plus 5 squared. Same answer, different approach. Let's take a look at one more. This one's a little more interesting. 9a squared minus 12a plus 4. This is actually number 46 in your textbook. Right away I can see that the first and last term are squares. The first term is 3a all squared. because 3a squared is the same as 3 squared a squared. Well, 3 squared is 9, so 3a squared is 9a squared. The second term can be written as 2 times 3a times negative 2. And the last term can be written as negative 2 squared. If you can see that, then you can rewrite this as 3a minus 2 all squared. If you can't, then just use the other method. Anything common to 9a squared, negative 12a, and 4? Nope, just 1. So I can go right in and find my product and my sum. My product is 9 times 4, which is positive 36. My sum is negative 12. Notice that since my sum is negative, I'm either going to need a larger negative number than a positive number, or two negative numbers. My product is positive, so I'm going to have to use two negative numbers. I can either have negative 1 times negative 36, or negative 2 times negative 18, or negative 3 times negative 12, negative 4 times negative 9, negative 6 times negative 6. When I add these together, I get negative 37, negative 20, negative 15, negative 13, or negative 12. My sum was negative 12. So these are the two numbers I need to use to rewrite the middle term. I had two negative 6's. My first and last terms don't change. My middle term becomes minus 6a minus 6a. What's common to these two terms? A 3 and an a. And what's left over is 3a minus 2. 3a times 3a is 9a squared, and 3a times negative 2 is negative 6a. Minus, what's common to these two terms? 2. What's left over? 3a. A negative times a positive is a negative. A negative times a, I need to get a positive here, so a negative times a negative is a positive. Negative 2 times negative 2 is positive 4. What's common to these two terms? That's 3a minus 2. And what's left over? 3a minus 2. Because these two factors happen to be the same, absolutely the same, I can write this as 3a minus 2 times itself, or 3a minus 2 squared. This whole section, 6.4, the difference of two squares and perfect square trinomials, are just exercises in a couple of special cases. The thing I'd really like you to take away from this section is that there are some special cases, but that you can factor them using the same techniques as you use for any other trinomials. If it turns out they're not factorable, well then they're not factorable. But if they are, you can use the same technique to find out what those factors are, no matter what the trinomial is that you start with. Or in the case of a difference of two squares, no matter what your difference of two squares looks like. This is question number 62 in your textbook. What's the greatest common factor of all three of these terms? Does anything go into 12, 36, and 27? Well, at least 3 goes into all of those. And if that's not big enough, we can check in the next step and see if there's anything else that goes into all three terms. I have 2 copies of x here and only 1 here, but I don't have any here, so there's no x in my greatest common factor. I have one copy of y in this term, 2 in this term, and 3 in this term. The biggest number I can take out of all three of them is one copy. What's left over is 4x squared, because 3y times 4x squared is 12x squared y. What's left over in this term is 12xy. 3 times 12 is 36. Times x, y times y is y squared. In this term, I need 9y squared to multiply by 3y to get 27y cubed. Now let's look again. Is there anything common to all three of these numbers? No. 3 was the biggest thing. What about the variables? I have one x and one y in this term, but I have no y's in this term, so y is not common to all three, and I have no x's here, so x is not common to all three. 3y is my greatest common factor. Let's figure out how to rewrite the second term here. To do that, I need my product and sum. My product is 4 times 9, which is 36. My sum is a negative number, negative 12. To get a positive product, I can either multiply a positive times a positive. When I add those together, I'm going to get a positive. Or I can multiply a negative times a negative. And when I add two negative numbers together, I get a negative result. So I need to multiply negative 1 times negative 36, or negative 2 times negative 18, negative 3 times negative 12, negative 4 times negative 9, or negative 6 times negative 6. My sums are negative 37, negative 20, negative 15, negative 13, and negative 12. The negative 12 I was looking for comes from adding together these numbers. So that's how I need to break up my middle term. What I have 12 copies of here, though, is xy's. So I'm going to rewrite that as negative 6xy minus another 6xy. Now I can look for the greatest common factor of the first two terms and the last two terms. What's common to 4x squared minus 6xy? There's a 2 in both 4 and 6, and there's an x in each of the terms. There's an extra copy of x here, but I can't undistribute a second copy of x because there's only one copy here. And there are no y's in this term, so I can't pull any y's out. 2x times 2x gives me 4x squared, and 2x times 3y gives me 6xy. This sign comes down, and I can look for the greatest common factor of these two terms. 3 goes into both 6 and 9. There's an x here, but not here. There's a y here, and although there are two y's here, I can only undistribute one copy. What's left over is 2x minus, because a negative times a negative is a positive, 3y. The greatest common factor of these two terms is 2x minus 3y. What's left over is 2x minus 3y. This polynomial, factored, looks like this. That's it for 6.4. We're not going to be doing 6.5 in this class, the sum and difference of two cubes. There are shortcuts for that as well. Unfortunately, with the sum and difference of two cubes, you really do need to recognize the pattern and be able to take the shortcut. It's a handy skill to have, but it's not absolutely essential. You might see it in future classes, but it should be something that you can pick up along the way. So the next lecture is 6.6, a general review of factoring. Well, that's pretty much what we've been doing all along. So the focus in that section is determining what type of problem it is so that you can use the appropriate technique. For us, that doesn't really matter, because we know that you can use the same technique for all of them. But there are a couple of things we need to look out for, so it'll be good practice and a good way to round out the sections on factoring. There are two more sections beyond 6.6. In 6.7, we look at a particular use of factoring to solve a particular kind of equation. And in 6.8, we'll look at some applications.